In this lesson, we're looking at the sum of sine and cosine functions. Now, way back in year 11, we already looked at how we can add functions together. So we've already got a workaround for graphing things like this. But in this lesson, we're going to take that a whole lot further and use this to actually solve equations as well. So the starting concept is just that when sine and cosine curves, or any multiple of them, are added together, the result is still a sine or a cosine curve. We'll call it a wave, something that continues on like this. But it's been dilated vertically. That means it's been stretched upwards, and it's been translated or slid horizontally. Now, what does this mean? Well, we'll have a look with an example here. This is something we should be able to graph quite quickly and easily already, and we can use this to understand the concept. So if I use two colours here, let's graph y equals sine x in blue, and we're going, just put my key points in here. Just a rough sketch will be good enough here. We've got something that looks sort of like this, and that is y equals sine x. Now let's graph y equals cos x in green. So we'll start here, come down like this, down to this point here, something roughly like this. Okay, and this is y equals cos x. Now, if we're adding sine x and cos x together, then if we've graphed each of these two graphs, we want to add the y values. And we've already seen how to do this. So we'll graph the combined graph in, well, let's go in black. So here, adding 0 and 1, I get 1. So let's look at the easy points first. Here I've got 0 and 1, so that's 1 again. Down here I've got 0 and minus 1, so that's going to give me minus 1. And here again, the same thing. And back here, 0 and 1. So I've got these definite points. What about these crossover points here? I can see that when x is pi on 4, the sine of pi on 4 and the cos of pi on 4 is both exactly the same. It's 1 over root 2. So if I add together 1 over root 2 plus 1 over root 2, I get 2 over root 2. And that's actually just root 2. And what I get is this height doubled. And this will be root 2. And so I've got my curve coming up through here and then down. And similarly down here where I've got minus root 2 and minus root 2, I'm going, minus 1 over root 2 and minus 1 over root 2, I'm going to get minus root 2, something around about down here. And my curve's doing something like this. Now, where our curve is equidistant up as it is down here, it's going to have a 0, and that's going to happen exactly here at 3 pi on 4. So it's going to come down through there, like that. And then it's going to come up and similarly go exactly through this point here, which will be 7 pi on 4. So here we have our black curve, y equals sine x plus cos x. And we worked it out by graphing y equals sine x, y equals cos x, and then adding y values together. And that was a perfectly good way to do it. But now we can see that this black curve that we've got here could be described as a sine curve or as a cosine curve. Let's have a go at doing it both ways. Now, if I wanted to call it y equals sine of something, right, you can see here that instead of having an amplitude of 1, ours has an amplitude of root 2. And that means that I'm going to write that number here because we've already seen that when we've got y equals something sine x, this something is the amplitude. I can also see that it's been moved across a little bit. So if I'm comparing this black curve to the blue sine curve here, you would say that the sine curve has got its first maximum turning point here at pi on 2, whereas my black curve has its first maximum turning point at pi on 4. So it's actually been shifted, the black one, across pi on 4 units from where the sine curve is. Now, how do you make a translation of going left pi on 4 units? You just add pi on 4. So this now is a formula for the exact same curve as this black one. It's just written a different way. Now, can you think of any other way that I could have moved it? What we can tell is that because we've added two curves that both have a period of 2 pi, our curve still has a period of 2 pi. Okay, that's important. But what we've seen here is that if we're going to move pi on 4 units to the left, is that the same as moving a certain distance to the right on a curve that repeats? Absolutely it is. How far would you have to move to the right to get the exact same thing? let's think about it. You'd still have your same amplitude. Sine of x minus something. How far would you need to move to the right? Well, if the period is 2 pi, how many quarters of a pi is that? 8 quarters. If you're going to move 1 quarter to the left, that's the same as moving 7 quarters of a pi to the right. Now, these two are exactly the same curve. If you're not completely sure, type these both into Desmos and just check that they graph up to exactly the same thing. Now, we could also have called this a cos curve, and there's going to be two versions of them. They're still going to have the exact same amplitude. Now, why can we describe this curve as sine or cos? Because sine and cos are basically the same curve, just shifted across. So we can easily describe them either way around. Let's have it as x plus something and x minus something, and let's see how we go here. Well, if we're comparing our black one to the cos curve, which is the green one here, its amplitude is stretched out, so it's been dilated vertically with a factor of √2. But if we wanted to see how far to the left it's been moved compared to this green one, have a look for a known point. For example, our green curve has its maximum at 0 and 2 pi, whereas our black curve has its maximum at pi on 4. So you can see here that for the black one to be compared to the green one, you'd have to say we've either moved it to the right, pi on 4, or to the left, 7 pi on 4. Now, moving to the left, that's going to be, where's my colour? Adding, so we'd have 7 pi on 4 here, and we'd have minus pi on 4 there. Now, these four are all the exact same graph as this one. But what we can see here is that there's 4 separate ways that we can represent this, depending on whether we choose to compare it to a sine curve or a cosine curve. Now, we can verify that any of these are actually the same as that by typing them into a program like Desmos and just checking that they graph the same. But we can also check them algebraically really easily. So let's check this one here using that compound angle formula. √2 sine of x plus pi on 4 is equal to, now I'm going to take the √2, keep that there, and then I'm going to put some brackets. Now remember that the sine of something plus something, you've got those results on your reference sheet. The sine of two angles added together is the sine of the first angle multiplied by the cos of the second one, plus the cos of the first one multiplied by the sine of the second one, and we have that. So then we get √2 multiplied by, well, the cos of pi on 4 is 1 on √2, so we've got 1 on √2 sine x, and the sine of pi on 4 is also 1 over √2, so we've got plus 1 over √2 cos x, and when we multiply √2 by both of these terms, the √2's will cancel, and we end up just with sine x plus cos x. So sure enough, we can be convinced that this and this do equal each other, and we can perform the exact same proof with any of these other forms to show that they all come out the same. So now let's come up with a nice general rule for what we've just seen. Any function of this form, y equals a sine x plus b cos x, notice that the x's are the same angle for both trig functions, where a and b are constants and they can't both be 0. Any function of this form can be expressed in any of these 4 forms. So you can take your pick, use sine or use cos, and then you can choose the sum or the difference of your angles inside there. Now, r is always greater than 0. That's the number that's out the front here. So we never get a negative out the front. And the reason for that is the formula for r is it's a squared plus b squared all inside a square root. Now you'll notice that a and b come from here and here. So as soon as you look at something in this form, the first thing you can work out is you can use that a and that b to figure out what b r will be. And in that last example, a and b were both 1, weren't they? And sure enough, 1 squared plus 1 squared is 2, and square root of 2 was the number that we had out the front there. Now, a note here, r is the same for all 4 forms. So you can work that out first and toss it into any of these that you like. But the alpha, this angle here that you use, that will vary depending on which of these forms you've used, and you've got to work it out specific to that form. Okay, so here is a series of steps that we can follow when we want to graph functions using this auxiliary angle method. Now, it's called the auxiliary angle method because that angle alpha that we're adding in the brackets to x or subtracting from it is called the auxiliary angle. Now, step 1, we can calculate R first up. That's really easy. You just take your A and B, square them, add them together, and take the square root. Step 2, choose one of those 4 forms. Now, you can literally pick whichever one you want. You'll find as you do more of these that sometimes a certain one lends itself to a calculation that's a little bit easier, but all of them will work out. And sometimes in the question, they'll tell you which one to use. Step 3, expand the form that you chose. So expand it out using that double angle formula, and those are on your reference sheet, so that's quite straightforward. And use your R value that you've already found in the expansion. Next, you want to equate the coefficients of sine x and cos x. Now, I'll show you how to do this in a moment. And use these to find what that auxiliary angle will be. Now, a couple of things that I've noted here. You want to pay attention to its quadrant by using both of the results. And that's because the sign, like the SIGN, of sine x and cos x will tell you which quadrant it's in. Now, you can work in degrees or in radians. Just make sure your calculator is in the right mode. The question will often tell you how they want you to work. But if you're working in, say, degrees, and it says find this to the nearest degree or the nearest minute, and you've got an awkward answer that's actually just an approximation, jot it down, sure, but we don't want to round off our answers and then do something with them and round them off even more and end up being really inaccurate. So store them in your calculator. Use those red buttons A, B, C, D, E, F, and jot down beside your working which red button you've used. Step 5, rewrite your function using your chosen form, one of the 4, the R that you found way back up here, and the alpha that you've found here. And now you can go ahead and graph that. So let's have a look at this in an example. Now let's run through those steps with an example. We need to express y equals 3 sine x minus 4 cos x in this form. Y equals r cos x minus alpha. Then graph the function showing the x-intercepts and the turning points to the nearest degree. So there's a hint that we not only need to work in degrees, but that we might need to round some things off. Okay, so let's start by calculating our r value. R is the square root of a squared plus b squared. So we can put those in like that. And what we get is 9 plus 16 is 25. Square root of 25 is 5. So nice simple r value for this one. Next, we can go ahead and take our form. Now, it's up to you if you want to write the y at the start of it. I tend to leave the y off. You'll see why in a moment. You can take it off or put it on, because really what we're wanting to do here, sub in our r, we should put 5, not r, because we know what that is now. Now, I want to expand this out using the double angle formula. Now, you can write another equal sign and put the expansion of all of this here, or you can leave the y off completely, or you can write y equals and now put the expansion of this right underneath. That way you've got one version of it, another version of it, and then a third one. Whichever way you do it, it's up to you. There's a bit of variety there. But one thing you are going to do, once you've done this a couple of times, is you're not going to do it the way I'm going to. I'm going to show you first so that you're not confused, and then you'll see what I mean. 5 lots of. Now, the expansion of this has got 2 parts in it. So we could do 5, bracket, and then put the 2 parts inside. Those 2 parts will be the cos of x times the cos of alpha plus the sine of x times the sine of alpha. And you can see there that you're always going to have 2 terms like this when you do one of these expansions, and that r value is always going to sit at the front of both of them. So rather than write this line and then expand out again to expand our brackets, you're going to start taking these time-saving shortcuts here and just put the 5 out the front of both of those bits, and that way you don't need any brackets. If you want to do that extra line, feel free, but I think you're quickly and easily going to get to that point. Okay, next thing to do is equate the coefficients of sine x and cos x. So have a look carefully and say, all right, here we've got 3 sine x's. How many sine x's have we got here? So look for where sine x is. Here it is. Now, how many sine x's have we got? Well, we've got 5 times sine theta of them, because this term is 5 sine theta sine x. Doesn't really matter what order they're written in. So what we can see then is that 5 sine theta, which is our coefficient of sine x here, must equal 3, because that's our coefficient of sine x up there. And we can write the other one at the same time. How many cos x's have we got? Well, we've got 5 lots of cos theta of them. 5 cos theta, alpha, equals -4, because that's the coefficient of cos x up there. Okay, now we can fiddle with both of these and say sine of alpha must be 3/5 and cos of alpha must be -4/5. Now, think about the quadrants. If sine is positive and cos is negative, which quadrant are we in? All stations to central. We must be in the second quadrant. So jot that down somehow so that you've thought that through. Now, how do we calculate alpha? Well, we've got two choices. We can either put in inverse sine of 3/5 and we will get 36.86. It's a big long one, and they did tell us we'd need to round it off. So the inverse sine of 3/5 would give us about 37 degrees. Or if we said, no, let's do the inverse cos of 4/5, not negative 4/5, just 4/5, we'd also get 37 degrees. Now, remember that if we're looking for an angle that's in the second quadrant, the best thing to do is say the related alpha, not alpha itself, but the related alpha is, and then take your pick. You could actually put the inverse sine of 3/5, or you could put the inverse cos of 4/5. And what we found is that it was 37 degrees to the nearest degree. Now, that is not our alpha. It is our related alpha. Our alpha sits in the second quadrant, so therefore we can say alpha must equal 180 degrees minus that. Now, you wouldn't necessarily write that out. You could just jump in and do 180 minus your answer on your calculator, and we've got 143 degrees, again to the nearest degree. Okay, what are we going to do with that? Well, now we can come back up here and say, hey, we've found our alpha. We know what goes there. So we've got a better version of this now. We can say, therefore, y is equal to 5 cos x minus 143 degrees. And we've acknowledged that we've rounded this off to the nearest degree. Okay, so now to sketch this, it might be handy to do a little mud map type sketch first and then do a proper sketch over here. Now on my proper sketch, I can see that my amplitude needs to be 5. So I've got those two marks there. We're marking this out in degrees, so we want to show at least 360 degrees of it. Now, if I just do a mud map sketch here of what 5 cos x looks like, it starts high, doesn't it, and goes down, and then comes back up again like that, and that would be 360 degrees at that point. This point here would be 180, this would be 90, and this would be 270. So that's something that I know, all right? So now I just have to make a transformation where I'm moving this, which way? To the right, 143 degrees. So that means that this high point here is going to be not when x is 0, it's going to be when x is 143 degrees. So let's pick a random spot here, call it 143 degrees, and make our high point. Okay, this low point here, 180, I need to move that also 143 degrees to the side, so that's going to take it over to, say, 323. So let's bring that over here. 323, that's going to be my low point, which will be down here somewhere. And my intercept here is at 90 normally, but if I'm moving at 143, then it's going to be at, what, 233? So that's going to be halfway between the high and the low, so obviously marking those and making a spot here. It's doing something like this. Okay, now to go from one intercept to the next, I know that happens every 180 degrees, so I can just take 180 off this 233 and I'll get 53. Put that in there. And I know it's going to be 360 degrees between one low point and the low point before. So if I do 323 and I subtract 360, I'm going to have minus 37 over here. And that's where my low point's going to be. It's going to come across something like that. Now I have to show x-intercepts to the nearest degree and turning points. So there's minus 37 and here's 143 degrees. So I've done everything that my questions asked for and I've graphed at least one full period of the curve. Now this question didn't actually ask me which domain to use for my graph. So I thought it was sensible just to graph one full period. But if the question had said make sure your graph goes from minus 180 to 180, then I would have continued my curve further over here and I would have found this point over here by just subtracting 180 degrees from it. Or if it said go from 0 to 360, well, I've almost got it there and I'd just fill it in. So have a look at the domain, and if it doesn't list it, choose something sensible.